Okay, in the previous vignette, we derived, yeah, I think it's fair for me to say we derived the Navier-Stokes equations. The reason I call them equations is that, as you can see in the box, that's a vectorial equation, so that's three equations. There's like an equation for the V1 component, the V2 component, and the V3 component. So we derived the Navier-Stokes equations, and and we did so by following what I've referred to affectionately as the continuum theory protocol. I say affectionately just because, I feel very inspired by the unity of things. And, if you want to see a great example of that in the Feynman lectures on physics, he has a really nice treatment of resonance. Resonance is a ubiquitous phenomenon that is not peculiar to pendula, kid on a swing. It's not peculiar to artificial mass spring systems. It's something that, all sorts of different phenomena exhibit resonance, like Lake Wakatipu in New Zealand. And so he also has a section where he talks about, meaning Feynman, talks about all the ways that Laplace's equation comes up. And so I really like that unity, and I'm trying to say that this continuum theory protocol that I've offered in the course is is one of these points of unity, in the same way that the statistical mechanics protocol gives that point of unity. It's mind blowing that for thinking about equilibria, whether the equilibrium of a piece of iron and its magnetic behavior, or the ionization state of the atoms in a star, those are all described by the Boltzmann distribution. That's and the same statistical mechanics protocol. And I don't know. I mean, each of us has to decide for ourselves how we feel about things. But I personally am deeply moved by this kind of unity that science brings to phenomena. And of course, I'm very happy with acknowledging the diversity of the living world, and I love it. And it's one of the reasons I love to travel and love to sort of quote William Blake, to see infinity in a grain of sand. That's fine, and I'm on board with that. But from a scientific perspective, I'm much more moved by the unity of things, I would say. And somehow, so the continuum theory protocol gave us a look at that. So what we're going to do in this brief vignette is we're going to turn to the subject of the Reynolds number and the dimensionless representation of the Navier-Stokes equations. And what I'm going to do is I'm going to basically walk you through this, and we're going to do it systematically. So the first thing we're going to do is we're going to take this equation that you see up here in the box, and I'm going to divide by rho. That's it, the density. So in so doing, what I end up with is this new version of Navier-Stokes. And note that I'm going to sometimes refer to eta divided by rho as the kinematic viscosity. I really don't know if I'm going to do that or not. I can't really tell, but likely I'll stick with eta, and we'll have it in this form. So what do we need to do when we want to introduce dimensionless variables? I did this earlier in the term when, even talking about exponential growth, I had dn by dt is equal to kn. And I said, well, fine, but in fact, k is 1 over a time scale, and so k times time is a dimensionless version of time, and somehow this whole idea of dimensionless variables, it's deeper than that to my mind. And the reason I say that is dimensionless variable is a way of thinking about the natural variable of a time, of a problem. In other words, when I was talking about exponential growth, the natural variable there is 1 over k. And so that's the units in which I should measure time. And so here what we're going to do is I'm going to say that there's a characteristic velocity. And, sorry for being self-referential, but, I want you to think of me swimming. So I'm swimming at roughly 2 meters per second or something like that if I'm swimming really fast. And so the characteristic velocity of a human swimmer is of order 1 or 2 meters per second. It doesn't matter, it's just some characteristic scale. And notice that the actual velocity can be written in terms of the dimensionless velocity times the scale. Or said differently, an alternative way of writing it is to say that v star is defined as v over this characteristic scale. I can do the same thing for position, where I say that the position is defined in terms of the characteristic length. The characteristic length of me when I'm swimming is my body size. And so I've got a dimensionless velocity, I've got a dimensionless position, and from the dimensionless velocity and position, I can get a dimensionless characteristic time scale, which I show you here. So this is the characteristic time. So what we're going to do is we're just going to look at these four terms, and each one of them we're going to rewrite it in its dimensionless variable. So let's take number one. So number one is dv by dt, and all I'm saying is I can rewrite that as d by dt star times uv star, which is the velocity, and then dt star by dt, so it's basically the chain rule. And what I'm left with is this very nice simplified expression, which is that the characteristic dv by dt is given by u squared over L, and then times dv star by dt star, which is dimensionless. This part is dimensionless. Okay, cool. So that's the first one. The next one is this nonlinear term, the gradient velocity term, and I can just do the same game. So I replace the vi with u times vi star, and then I replace the d by dx with d by dx star, and then using the chain rule, I multiply that by dx star by dx. And the velocity I've replaced by its relevant dimensionless variable. And so when all the dust settles, I'm left with u squared over L times the dimensionless gradients of velocity. I can keep going. So now let's do the third term, which is I have minus 1 over rho d gradient of p, and I can replace this d by dxi with its dimensionless analog, which you see here. And so I'm left with this object, but note that the numerator, the pressure, still has units, and I can absorb that by defining the pressure, a dimensionless pressure, in this way. If I do that, then I end up with this nice expression. And finally, I can tackle the last term, which is eta over rho, and then the Laplacian of v. I'm going to do the same thing. I'm just going to, everywhere that I see an x or a v, I'm going to replace it with its corresponding dimensionless analog, and then I'm going to do the accounting. And when I do, this is what I find. So we're ready to put it all together. So that's what I do here. So here, I'm doing nothing more than taking the result of the four terms we just wrote down, and everywhere that I have them, I'm basically I'm replacing them with their starred equivalents. That leads to this very, very provocative form that you see right here. Okay, so what we've done is we've multiplied both sides by L over u squared, and that leaves us with this simple expression. And you can see here that I can rewrite this in this so I introduced this so-called Reynolds number that dropped out of the dimensionalization of the equations. In other words, this quantity is forced upon us. It's dimensionless, and it was forced upon us by our attempt to render the equations dimensionless, which we did. So we've got this Reynolds number, and now the Navier-Stokes equations can be written in this dimensionless form. And what you see is that the Reynolds number tells us about the relative importance of the terms on the right relative to the terms on the left. Another way of saying those words is that the Reynolds number gives us a measure of the relative importance of inertial terms versus viscous terms. So, you know, if I push off the wall in a pool with my arms out like this, the inertial terms are dominant. And what do I mean by that? I mean that my Reynolds number is big, and it means that I'm entraining a bunch of fluid, and it means I can propagate across half of a 25-meter pool underwater without a breath and without pushing, without swimming, without doing anything. No propulsion. If you look out into the ocean, I'm looking out in the Pacific right now here in San Francisco, and just saw a freighter coming in. You know, this giant ship, if it's traveling at full speed and then it turns off its engines, it's going to take a long time to stop. On the other hand, if a bacterium turns off its flagellum, it's going to stop in a distance smaller than the diameter of a hydrogen atom. You know, kind of crazy. And so it's the Reynolds number that tells us about that. So let's actually look at that. So here's an example, E. coli swimming. So the characteristic velocity is 30 microns per second is the typical velocity. I just know that because they travel about 30 body lengths in a second. The length scale is the size of the cell. So that's 1 micron, 10 to the minus 6 meters. The density of water is 1,000 kilograms per meter cubed. And the viscosity of water, as we already said earlier, is 10 to the minus 3 Pascal seconds. And so what you can see is that we get 30 times 10 to the minus 6, or a few times 10 to the minus 5. This is known as the low Reynolds number limit. The world of cells is the low Reynolds number hydrodynamic world. So that's an important consideration to keep in mind. As I was saying a minute ago, if I take a human swimmer like Michael Phelps, 2 meters per second is the swimming speed, 2 meters is the characteristic dimension, 1,000 kilograms per meter cubed is the density of water, 10 to the minus 3 Pascal seconds. And that says that the Reynolds number in this case is of order 4 times 10 to the 6, so much, much bigger than 1. The Reynolds number 1 is the dividing line between kind of different phenomenologies. If I'm in the low Reynolds number limit, then I'm going to basically, going back to our equations, if I'm in the low Reynolds number regime, I'm going to ignore these two terms. We're just going to ignore them. We're going to drop them all together, because if Reynolds number is very small, these two terms are large in comparison with the ones on the left. And you can calculate that. You can keep the terms and show to your own satisfaction that the terms on the left are small in comparison with the terms on the right. So if we keep only these terms, that's going to be the limit of what we refer to as the Stokes equation, and that will be very interesting and relevant. So as I was trying to say, the Reynolds number kind of separates these regimes. Last one I wanted to say was the bar-tailed godwit, which is this bird that flies 10,000 kilometers between Alaska and New Zealand in a continuous 10-day journey. And the Reynolds number here, the velocity is about 10 meters per second for these birds. Their characteristic scale is, let's say, 10 centimeters. The density of air is 1 kilogram per meter cubed. And the viscosity of air is about 100-fold smaller. And so, once again, we find that they have very large Reynolds number. They're in the large Reynolds number limit, which means that drag forces, that the inertial forces are significant in a case like this. So I think that that's the main things that I wanted to say, just as a first cut introduction to the Reynolds number and to the dimensionless form of Navier-Stokes. And now we're basically ready to try to use these equations to look at a fun and interesting problem. And what we'll do is we'll think about the amazing Kara.